Okay, this is a video about sampling distributions for a sample mean. Now, the nice thing about this point is that you have seen the idea of a sampling distribution multiple times. We're just going to apply this to a quantitative sample where you take the mean of all of the items in the sample. So you're taking a sample of size n, okay? And you're going to add up all the values in that sample, you're going to divide by n, and you're going to get a mean value. Okay, so it's x bar, which is the sample mean, as opposed to mu, which is the population mean. Okay, so you take this sample of size n, you get the sample mean. Now, you keep taking different samples of size n, you're going to get sample means that are going to be near each other, but not all the same. There's going to be some variation in the sample, and they're going to make a distribution. And generally speaking, that distribution of the sample means, so the sample mean is going to be distributed, and the mean of the sample means should be near the population mean. So this means that I have an unbiased indicator. The sample mean is an unbiased point estimate of the population mean, so the mean of the sample means, yep, we're actually calling it the mean of the means, the mean of the sample means is equal to the population mean. Okay, so this thing is going to be distributed around the mean. Now, if my 10% rule holds, right? So if my 10% rule holds and the sample size is less than or equal to 0.1 of the population size, then I get an estimate for the standard deviation for the sample means. So the standard deviation for the sample means is going to be written as the standard deviation, or the sample means, will be the square root of the standard deviation of the population mean over, sorry, that's not correct, will be the population standard deviation over the square root of n. Okay, so that's going to be the second part here, right? Over the square root of n. Now, our hope is that this distribution will be normal. Okay, and just like you had a 10% rule here that guarantees the standard deviation, we used to be able to use the large counts criteria when we were working with proportions to establish normalcy. We no longer have a large counts criteria because we're not working with proportions. Proportions got us to binomial, which allowed us to approximate normal for large counts. So we have to look at, how do I get normalcy? So there's two paths to normal. Okay, so for the mean. So we're going to take a look at those two paths now. Okay, so two paths to normal. Sounds like a self-help book. Two paths to normal. One is the measurements of the population are normally distributed. So what would be something that would be normally distributed? Like the heights of people in the population, their weights in the population, things like that would be normally distributed, bell-shaped and symmetric. If the population is considered normally distributed, then we're in the running. Then we know that once I get the 10% rule, the x bars are going to be distributed normally around the mean of the population, and with the sigma, the standard deviation of the population over the square root of n. Okay, so that would be great. The second pathway here is what we call using the central limit theorem, CLT, the central limit theorem. And this is kind of like one of the great ways that we can do inferencing. If my sample size is greater than or equal to 30. So this is going to kind of like be similar to the idea of a large counts, right? The law of large numbers starts kicking in, and I get this central limit theorem, which tells me that the distribution of the samples will also be distributed normally with a mean of the of the population with standard deviation over the square root of n. Now, so this is still dependent upon 10% in both of these cases, right? These two are still dependent upon 10%, but the normalcy here comes from CLT. The normalcy here comes from the normal distribution. So you would get bell curve, mean at mean, standard deviation as of x bar, mean of x bar is at standard deviation over square root of n. Now, why does this work? Okay, a simple example of this is to take a 6-sided die. Okay, your outcomes are 1, 2, 3, 4, 5, 6, and they're uniform. There is no central tendency in this. There is no sense that like 3 and 4 are going to come up more than 1 and 6. They all come up the same amount. However, as you start rolling the dice and you start taking averages, those averages are going to start approaching 3.5. Okay, and the more dice you roll, the closer you're going to get to 3.5 with those averages. And the more likely, it's more likely to be close, those averages are more likely to be close to 3.5 than they are to 1 and 6. I mean, yes, you could roll a die 30 times, right, and get a 1 every single time, and the average would be 1. It is not very likely. Same thing with 6. You could roll a die 30 times, get a 6, and every time it comes up as a 6, but it's not very likely. But chances are, if you roll a die 30 times, you're going to get approximately 5 of each of these, right? If you got 5 of each of those, you're going to get around 3.5. Now, you might have a few on the high side, you might have a few on the low side. That's why you're going to get a bell-shaped curve. This is why central limit tendency happens. Ultimately, this is probably the best example to define this, because the worst case scenario would be it's uniform, right? If it's uniform, why do I get a bubble or a bell shape when I take the means? And this is kind of demonstrating it here. It's really hard to get just ones on the outside. It's more likely that you're going to get a mixture of all the numbers, which means that the mean of your sample is probably going to be pretty close to the expected value of the experiment. All right, so there you go. This is our kind of overview of sampling distribution of means. 10% gets you the sigma over the square root of n. 2 pathways to normal. One is that the population was normally distributed to begin with, which means I don't need my 30. But if the population is unknown or not normally distributed, once I get over a sample size of approximately 30, I start seeing that bell shape show up in my sampling distribution for the means. All right, so we'll talk about this next class.